Imagine dropping a single, concentrated droplet of blue ink into a glass of clear water. At first, you have a highly ordered, high-density cluster of molecules, but as time passes, thermal fluctuations cause the ink particles to collide randomly with water molecules. This is physical diffusion governed by thermodynamic entropy, spreading the ink until the glass is a completely uniform, lukewarm blue. Now imagine trying to reverse this process, to watch a cloudy glass of blue water spontaneously assemble itself back into a perfect, suspended droplet. In physics, this violates the second law of thermodynamics, but in the realm of computer science, reversing this exact thermodynamic dissipation is the key to creating mind-blowing, generative artificial intelligence. To understand how this physical concept translates to digital images, we must look at how computers perceive pictures. A standard 512 by 512 pixel color image lives in a massive 786 and 432 dimensional space, where every single coordinate represents the red, green, and blue values of a specific pixel. Within this infinite hyperspace of possible pixel combinations, the subset of coordinate points that actually look like real objects, like cats, cars, or human faces, is incredibly tiny, forming a complex, folded manifold. Traditional generative models, like generative adversarial networks or GANs, tried to map a simple distribution directly to this complex manifold in a single massive jump, which often resulted in highly unstable training sessions and collapsed modes. Diffusion models, pioneered by Jascha Sohl-Dickstein in 2015 and refined by Jonathan Ho in 2020, solve this mapping problem by breaking the journey down into hundreds of tiny, manageable steps. In the forward process, denoted as Q, we start with a clean image, x0, and systematically inject tiny amounts of Gaussian noise over a sequence of, say, 1,000 steps. This is structured as a Markov chain, where the state at step t depends only on the state at step t-1, scaled by a variance schedule parameter called beta t. By the time we reach step 1000, the original structure of the image is completely destroyed, leaving us with nothing but isotropic Gaussian noise, representing a state of maximum entropy. Now, calculating this forward chain step by step for 1,000 iterations during model training would be computationally disastrous. Fortunately, we can bypass the entire intermediate sequence using a brilliant mathematical shortcut known as the reparameterization trick. By defining a new variable, alpha t, as 1 minus beta t and alpha bar as the running product of all alphas up to step t, we can express the noisy image at any arbitrary step directly as a function of the original clean image x0 and a single noise vector. This closed-form equation means we can instantly sample a noisy image at step 500 or 800 during training without having to compute the preceding 499 steps, saving massive amounts of compute. Our goal is to learn the reverse process, denoted as p theta, which acts as a guide to steer us backward from pure noise to a clean image. At the heart of this reverse process is a specialized deep learning architecture known as a U-net, which features symmetric downsampling and upsampling pathways connected by residual skip connections. The U-net takes two inputs, the noisy image at step t and a scalar value representing the current time step t, which is encoded using sinusoidal positional embeddings similar to those found in transformer models. Instead of directly predicting the clean image, which is a highly nonlinear and difficult target, the U-net is trained to predict the exact noise vector that was added to the image at that specific step. Once the U-net is trained, we can perform the miracle of generation by reversing the flow of time. We start by generating a tensor of pure random Gaussian noise from a standard normal distribution. We then feed this noise into our trained U-net at time step 1000. The network predicts the noise component, which we scale and subtract from our current image, adding back a small, controlled amount of random noise to prevent the generation from getting stuck in local minima. We repeat this denoising step iteratively, tracking backward from time step t to t-1, slowly shaving away the random chaos. Over hundreds of steps, coherent structures, edges, and textures gradually crystallize out of the white noise, culminating in a pristine, novel image at step 0. But how do we control what the model generates? turning a generic image generator into a tool that responds to text prompts. This is achieved by injecting conditional text representations into the U-Net's bottleneck and attention layers, using cross-attention mechanisms, where a text encoder like CLIP processes the prompt. To make the model highly responsive to these prompts, researchers use a technique called classifier-free guidance, or CFG. During generation, the network performs two predictions simultaneously, one conditioned on the text prompt and one completely unconditioned. By calculating the difference between these two predictions and scaling it up, we aggressively push the generated image toward the prompt's features, allowing us to dial in how strictly the AI adheres to our written instructions. To bring this entire mathematical framework to life, we can look at a simplified implementation of the reverse sampling loop in PyTorch. We begin by initializing our starting tensor, x, with pure noise sampled from a standard normal distribution, matching our target latent dimensions. We then enter a loop that runs backward from our maximum time step, t, down to 1, tracking our position. In each iteration, we disable gradient calculations to conserve memory and pass the current noisy tensor along with the single integer time step into our trained U-Net model. The model outputs its prediction of the noise, which we subtract from our current tensor using the closed-form scaling parameters. If the time step is greater than 1, we inject a controlled amount of random noise back in before continuing the loop.